Thank you very much. It's a great honor to be here and to receive this prestigious award. Today, in the next 5 or 6 months, I'll tell you about my research that I've been doing in the last 2-3 years on porous materials. So porous materials are materials that have an empty space inside them. So the question that I'm going to address today will be why do we need this empty space inside materials, and what good does it do? So empty space has many different perceptions in different areas. For example, if you look at the arts, horror vacui, the fear of empty space, represents the filling of the whole empty space with the artwork. And if you look at in chemistry, molecules or atoms tend to pack in a so dense fashion that the empty space is minimized. So from an artist's perspective and from a molecule's perspective, empty space is a wasted space. But there are cases where empty space is not a wasted space. For example, in design, you may or may not have noticed this, but in the famous FedEx logo, there is a hidden arrow in the X, between the X letters. And this happens by arranging the E and X letters in an appropriate fashion. Another example is, for example, this TV channel's logo, the USA Network. For example, in here, there is no S letter. But when you modify the letter U and A in a correct manner, you can create this S letter between them without doing without doing anything in the positive space. So as a chemist, what I'm trying to do is I'm trying to design and create such functional empty spaces at the molecular level. And to do that, I'm using materials called polymers. Polymers are an important part of our daily life. For example, biopolymers, DNA, protein, they're essential to biological function and structure. Also, there are synthetic polymers where which has like a widespread usage in our daily life, and we rely on them pretty much on every product that we have. But one specific problem, if you want to create empty space inside the polymers, is when you use those type of materials, the problem is they are flexible. And when they are flexible, they tend to foil like proteins around each other, and they form this densely packed structure, which has pretty much no or little empty space inside itself. So the solution to that would be, if you use a rigid starting building block, then it might be now possible to create an empty space by appropriately arranging those building blocks at the molecular level. So in order to create those type of materials, I'm working on the type of materials called porous materials, which spans different type of materials like called porous polymers to other framework materials, which has little organization, as you can see on the left side, or they are much more nicely organized in a nice fashion, where you can see these empty openings, which corresponds to pores or empty spaces inside those materials. And you can think of those materials like a sponge that you use in your kitchen. So a sponge has a lot of openings and holes inside it so that it can absorb a lot of water. And the idea here is similar, but our pores are not at the macro level, but they are rather on the scale of nanometer. And with that scale, we can now do some functional chemistry for certain applications. And so this is what those materials could look like in the macro scale. Those are like nice crystal structures of them. And so if you take one of those crystals in a 1 gram scale, like just 1 gram material, it has the surface area which equals to 1.5 football field. So that means, if you can arrange like as many molecules as you can on a football field, that means you can put that much molecule inside 1 gram of this material. So there's like a lot of opportunities with that much empty space to do chemistry with those materials. And once we make those materials, the areas or the applications that we are trying to address or solve the challenges is in the area of energy, environment, and health. And then there are a lot of specific applications for those materials, but I'm going to highlight only 2 of them, the chemical protection and the diagnostics application using those materials that I've also been doing in the last 2 years. So for the chemical protection, for example, it's utmost important to make materials that can efficiently remove toxic chemicals, especially for like military purposes or for the occupational, like for the safety of the workers. So you want to use a proper material in a gas mask, for example, and that can efficiently remove those toxic chemicals. And we use those materials, we develop those kind of materials with a lot of empty space inside them, and we vary the chemical functionality at the bottom here so that we can improve their performance for specific chemicals. Another application is the diagnostic applications. So we can also use those materials to detect species in biofluids, for example, urine or blood, to detect certain diseases by looking at the concentration of like metal ions or like other chemical species in them. And to do that, we can install appropriate functional groups on them. And then, for example, in a mixture of a lot of things in a urine or blood, we can selectively and efficiently remove some of the species. For example, it's a copper ion, which is associated with Wilson's disease, for example, and then remove it from this the mess of mixture, and then detect it in vitro using those materials. So as I said, those porous empty space inside the materials have a lot of opportunities. With the design and the chemical functionality, we can make materials that were not haven't been able to be made before. So with that, I would like to take this opportunity to thank my mentors, starting from my master's to my current postdoctoral studies and the funding agencies, and thank you for listening.